So I think the stuff that we are doing is quite physicsy right now. It's a pretty it uses quantum mechanics instead, statistical mechanics, and that's why it's actually quite a lot of fun too. So I just make it 28. This was supposed to be the last time, but I think now this is working. I borrowed this pad from mine, so I think my pad just stopped working. Okay. So last time we were actually talking about two things. One was detailed balance. The other was this law of mass action, which sort of governs uh, equilibrium between forward and backward reactions. Okay, so we will apply the same ideas today to black body radiation. In fact, one of the most famous application of detailed balance is the fact that Einstein inferred stimulated emission from detailed balance arguments. Okay, so so let's get started. So in general, okay, so last time what we were talking about is the forward and backward reaction rates and cross sections are intimately connected to each other. For each elementary state connecting the reactants and products, you have some cross sections and rates. And in equilibrium, the rate at which you have the forward reaction and the rate at which the backward reaction happens balance each other. Okay, so so what it means is that the rate coefficients of the forward and backward reaction are proportional to each other. Okay, and what it means that since the rate coefficients are quantities which are independent of equilibrium, what it means is that the fundamental processes, the rates of fundamental processes are proportional to each other in the forward and the backward reaction. And detailed balance is what helps us determine the relation between these two rates. Okay, so we'll actually also do black body example. So let's consider, so how does a black body radiation arise, right? What are the minimum requirements for you to have a black body radiation? So you have to have matter, and the matter has to have some temperature. That matter radiates and produces photons just by its nature, and those produced photons sort of move around in that matter and exchange energy and momentum with the atoms of that matter. Okay, and this is what sort of creates matter and radiation in equilibrium, which is sort of a universal, which has universal properties, and those properties are sort of known as the black body radiation. Okay, so let's consider a simple example. So you have, say, a two-level system. So it's a quantum system where there are two states, U and L, and the degeneracy of the upper state is Gu, and the degeneracy of the lower state is Gl. Right. So, so if you have an electron in an upper state, and if it spontaneously decays to the lower state, it releases a photon of frequency nu or energy E equals h nu. So this energy of the photon that comes out because of this radiative de-excitation of an electron is nu, and h nu is equal to EU minus EL. Okay. So there are, if you think of this in terms of forward and backward reactions, you can actually think of it as XL plus h nu gives you XU. So you have an atom in state L, okay, and a photon comes, the atom absorbs this photon, and it excites the electron to a higher level. That's the forward reaction. This is absorption. The forward reaction is absorption of a photon, right? The reverse reaction here is spontaneous emission. Okay. So these are the elementary processes, right, which should equilibrate and give rise to a black body Planck function. What else is there, right? In addition to these two processes, there's also xu plus h nu, giving you xl plus twice h nu. This is stimulated emission, right? So if there is photon field present, and if you have an atom in the excited state, in presence of that photon field, the atom can de-excite to the lower level and produce two photons. That's why this is stimulated emission. You need a background photon field, this h nu, in order for stimulated emission to happen. Okay, and Einstein figured this out, that there has to be some fundamental process like this in order for this two-body system to produce an equilibrium photon spectrum which matches the Planck spectrum. Okay, so this is an instance of a macroscopic behavior hinting us towards some microscopic, very fundamental microscopic process. Okay. So then there are three elementary processes: photoabsorption, spontaneous emission, and stimulated emission. Okay. So in local thermodynamic equilibrium, right, the forward and backward reaction rates are equal. So you have NL. NL is the number density of atoms which are in the state L, right? So this NL is number of atoms in state L per unit volume. So NL times B, yes. Yeah, so this is an atom which has energy levels. Let's just consider two energy levels. Okay, so this is called a two-level system. Number density of atoms in which electron is in state L. Nu is the number density of atoms, the same atom, but electrons are in level U. So number density of excited state versus number density of ground state. So NL times BLU times U nu. So this is the rate of, so basically this is the rate of so you have, right. So this is the rate at which the atoms in state L, when exposed to radiation, gets excited. So this is the rate at which the ground state gets excited to the excited state. So this is actually equal to Nu times BUL times U nu. So this is basically, this is absorption. This is absorption, right? Because you have this radiation. So U nu is energy density per unit frequency in radiation. This is stimulated emission. Stimulated emission that populates the lower state. And there is, of course, Nu times AUL. So these are microscopic rate coefficients. Okay, these are called Einstein's A and B, right? This is Einstein A for spontaneous emission. emission. And the unit of A is basically probability per unit time, right? So what is the probability that an electron in an excited state spontaneously decays to a ground state, producing a photon of energy h nu? What is the probability per unit time? So if you wait for longer, you'll have more spontaneous emission. More photons will go to the ground state. Okay. Right. So in equilibrium, the rate at which the ground state is getting depopulated by absorption is equal to the rate at which it gets repopulated because of stimulated emission and spontaneous emission. That's what I'm writing here. Okay, and these are Einstein's A and B coefficients. Okay, so we can write, so using this equation, you can write U nu in LTE. Right? So this equation holds in LTE is nothing but, so we just we just bring this on the left and manipulate it so that you get NU AUL, excuse me, divided by NU BUL times NL by NU BLU by BUL minus 1, right? So this is what your photon energy density per unit frequency should look like in LTE. Now we know what is the photon energy density for a black body, right? We know U nu black body energy density. So always in radiation, you have to know what you're talking about. There are a lot of quantities like I nu specific intensity. U nu is related to specific intensity. So this is energy per unit volume per unit frequency. Okay, the energy contained in the photon field per unit volume per unit frequency. So this is equal to 4 pi by C times B nu. This is B nu is this black body function, which is a function of temperature, right? So what I'm saying is this quantity here has to be equal to this, right? And we know what B nu is. B nu is the Planck spectrum. So this is equal to 4 pi by C times twice h nu cube by C squared, 1 over e to the h nu by kt minus 1, right? So this is the Planck spectrum, right? Twice h nu cube by C squared, 1 over e to the h nu by kt minus 1. So the ratio of these coefficients should be such that you get this function, right? This is the whole idea of detailed balance, that you can get the relation between forward and backward reaction rates and cross sections by demanding that it reaches the distribution function in LTE. So if you compare these two quantities, comparing this and this, you can easily say that A, so this of course NU just cancels. You can easily say that A UL by B UL is equal to 8 pi h nu by C cube, right? All we have to do is A UL by B UL equals this quantity, which is nothing but this, right? So this is how Einstein's A for spontaneous emission and Einstein B for stimulated emission are related. For any atom, this relation will hold. And in fact, if not just for two-level system, if you have multiple levels, and if you're connecting two levels through this sort of a microscopic reversible process, the Einstein's A and B will have to be related like this. Okay, and the second thing that we can actually see from here is comparing this and this. So NL by NU in LTE times BLU by BUL should be equal to e to the h nu by kT. Right? We are just sort of comparing the forms, and this has to be true for all temperatures. Okay. Okay. So the other thing is we know that if the atoms are in thermal equilibrium themselves, right, the excited state has a smaller number compared to the ground state. So NL by NU equals GL by GU times e to the UL by KT. We know this. This is just the Boltzmann factor, right? So the lower level has a low, L is a lower level. So it is exponentially more, it has a higher probability of being there. So this is always true. And we know that EUL equals h nu. The frequency of the photon that's emitted is equal to the energy by kT. So it's equal to energy by h, right? So if we plug this, so this is in LTE, of course, right? In a system where atoms collide with each other and are able to maintain the same temperature, this is correct. Okay, so if we plug this in, what do we get? We get GL by GU e to the EUL is nothing but h nu by KT, BLU by BUL UL equals e to the h nu by KT. In fact, the nice thing is this just goes away, and we have the relation between BLU and BUL, and which is actually quite simple. So GU BUL equals GL GL BLU. So these are how Einstein's coefficients are related. Where's the this one? Right. So once I give you AUL for a particular transition, you know BUL and BLU from this kind of detailed balance consideration. This is very, very fundamental. Here we are assuming that there is no broadening. You know, the line width is very thin. That's correct. We are assuming that the transition happens only at a particular frequency nu naught. We'll actually relax that assumption in a bit. So here we have done this exercise in terms of U nu, right? You know, we took the energy density in photons, but you can also do the same exercise equivalently in terms of something called N gamma, right? This is called photon occupation number. It's a dimensionless number, and this is actually defined as c squared by twice h nu cube times I nu. And this is always true. This photon occupation number can be calculated for any I nu. It need not be a black body radiation only, right? So this is what photon occupation number signifies is what is the average number of photons in a given state, right? And the state for a photon is sort of determined by its frequency. How many photons are there on average at frequency nu to nu plus d nu or something like that. Okay, so this is a number. So the equations that I just wrote down, so d by dt NL from transition from upper level to lower level, there are two things, right? When you go from U to L, one is spontaneous emission, the other is stimulated emission. So this is equal to NU times AUL 1 plus N gamma bar. Actually, we can also define N gamma bar as bar here sort of means that you're averaging over all solid angles. So n gamma bar is nothing but c squared by twice h nu cube times I nu bar. You have averaged over all solid angles. And we also know that u nu is equal to I nu bar by C. Just a second. So this is energy per unit area per unit time. So you when you divide this by C, you get the energy density, and then you multiply by 4 pi. Then you basically then you're sort of multiplying over all solid angles. So this is the relation between the photon energy density and the specific intensity or mean intensity. Right. So this is nothing but C cube by 8 pi h nu cube times u nu. So all these quantities, the photon occupation number n gamma or I nu or u nu are sort of related to each other. And you should be comfortable going from one to the other. Now, if we write these equations in terms of just photon occupation number, they become simpler. Like this is how it looks like, instead of those u nus and so on floating around. We wrote the same equation here. Right? Here we wrote these equations in terms of u nus, which is an energy density in photons. Here we are writing the same equations in terms of photon occupation numbers. And here we have used the fact that BUL and BLU are all proportional to AUL. Okay, so this is the these transitions from upper to lower state, and ddt of nu L to U is equal to NL times GU. This is absorption. This is absorption. GU by GL times AUL times N gamma bar. Right. So the second equation is basically these transitions. This is absorption of a photon, which kicks your electron from lower state to the higher state. And this is proportional to U to L, sorry. Right. So you are populating the upper level U because of transitions from L to U. Okay. And this definitely requires photon field. Right. This is a term which is due to stimulated emission. You can actually see this. Let's go back up. This is basically coming from this term, right? So there are two terms on the right-hand side. One is just NUAUL, which is this guy. This is just spontaneous emission. The second term, when you express it in terms of N gamma, this is what you get. And so the presence of N gamma there means that this requires a photon field to be present. Okay. And this first one is, of course, spontaneous emission. And this is absorption. And of course, absorption in this case will require photons to be around. If there are no photons, electrons cannot get excited to the higher upper levels. Okay. And these relations are true even in absence of LTE. Right? These are the microscopic rate reactions. These are true even in absence of LTEs. What LTE does is it relates AUL to BUL and BLU. And that's really the power of this detailed balance argument. Okay. So for LTE though, for local thermodynamic equilibrium, what we have is I nu bar, which is equal to B nu T, which is equal to twice H nu cube by C squared, 1 over e to the H nu by KT minus 1. Okay. So if we just look at the expression for N gamma bar here, right? What is N gamma bar for LTE? What you get is N gamma bar is equal to in LTE is equal to 1 by e to the H nu by KT minus 1. Okay. So in equilibrium, the photon occupation number is given by this. So, so when can you ignore stimulated emission? You can ignore stimulated emission when N gamma bar is much less than 1, right? If N gamma bar is much less than 1, you can ignore this relative to this term. When does this become much less than 1? It becomes N gamma bar is much less than 1 if at high frequencies, right? If H nu by KT is much greater than 1. Right? If H nu by KT is much greater than 1, you can just ignore 1 and it becomes e to the minus H nu by KT, which is much less than 1 because H nu is much greater than KT. So this is in the Wayne tail of black body. So the black body spectrum has a power law Rayleigh-Jeans part, and one of the biggest puzzles which led to quantum mechanics was that how do you avoid this UV catastrophe? Okay, and the way you avoid this UV catastrophe is by saying that photons are quantized. Photon has an energy equals to H nu. If you go to very high energies or very high frequencies at a given temperature, you do not have enough thermal energy to even create one photon. Right? So N gamma bar being much less than 1 means that it becomes extremely difficult to create a photon at high frequencies. Okay, so this is where Planck came up with this quantum of photon, this photon idea that light has a quantum nature, and a particular photon only has, can have a particular photon at frequency nu can have energy only E equals H nu. So as you go to very high frequencies, you cannot even create one photon. You don't have enough thermal bath energy to create even one photon. That's why you have this Wayne exponential cutoff. Okay. But in the Rayleigh-Jeans part, what happens in the Rayleigh-Jeans part, which is H nu? We'll actually change this to a new lecture once here. So H nu by KT much less than 1. In that case, N gamma bar LTE becomes, so this becomes e to the H nu by KT is just 1 plus H nu by KT, right? E to the X when X is small is 1 plus X. So N gamma bar becomes KT by H nu, which is much bigger than 1. So at low frequencies, a single frequency state can have many photons. Unlike a fermion, so photons are bosons, and in the single state, they can be in huge numbers of them. Unlike fermions, in a given quantum state, you can only have one fermion. So here in the Rayleigh-Jeans part, in the same state, there are many photons. So in radio astronomy, optical astronomy, and so on, you are especially in radio astronomy, you're almost always in the Rayleigh-Jeans regime, where a single state has billions of photons, and you can treat those as classical waves, right? All those gazillions of photons together sort of behave as this continuum where we can actually treat them in a continuum way. We don't have to bother about the photon nature or the quantum nature of light. But whereas in X-rays and gamma rays, where you go to high news, you're actually counting a single photon. That's the quantum limit. Okay. So these are very, very profound ideas. And actually, these are the kind of things that started quantum mechanics. Okay. So you should have intuitive feel for these concepts. Okay. So so we can actually recast BLU, this absorption, Einstein's B coefficient, which sort of quantifies absorption as absorption as an absorption cross section. Section. How do we do that? So d dt of nu. So the rate at which you are creating electrons in excited state because of absorption of photons is equal to BLU NL U nu, right? This is what we already used. This we can actually write it as, like in our standard form, when we are doing collisions, we wrote a specific form to calculate these rates, right? This is like a rate per unit volume, actually rate density, because N is per unit volume. So how did we write it? So the absorption is a two-body process, right? You have an atom in state L, and you have a photon, and they sort of interact with each other, come close together. So it's a sort of a collision. So you can write it as this rate as NL times d nu sigma LU function of nu times C times U nu by H nu. Okay, let's try to see what it means. So U nu is energy density of photons. U nu d nu is energy density in photons with energy nu to nu plus d nu. So U nu d nu by H nu is the number of photons with frequency nu to nu plus d nu. All right. So so this is nothing but n photons sigma times C. Right. Some sort of a this is like n photons, right? So this is, we are actually expressing it in terms of our collision language. Okay. If we assume this to be sharply peaked, that is, if we assume that the frequency of transition only happens at nu equals nu naught, very thin line width. If we assume that, then this is nothing but NL U nu C by H nu. We can get the news out because nu is actually constant, that transition frequency. That is integral of d nu sigma LU nu. So so just by comparing this and this, we can actually write sigma LU in terms of BLU, right? So B signifies the efficiency with which absorption happens, right? How efficiently the electrons in level L go up, get excited. So by reading it off, we get B Lu equals C by H nu integral d nu sigma Lu nu.
H by H. That
Hmm?
is like the number density
Mhm.
per
Frequency.
frequency. So we are saying that no photons can be created on this distance because you are taking that to be constant and taking out of the integration.
Right. So, right. So I am assuming that uh, the energy density in photons at that frequency difference is, basically this transition happens only when nu is close to nu naught. So this integral d nu is sort of like a delta function, integral over a delta function. Okay. So the point is this Einstein B coefficient and this absorption uh, cross section are sort of proportional to each other. Like, this we have seen in almost all the cases. You can use various things interchangeably. So now here is where we introduce this line profile, right? All this we were assuming like the transition to be sharp. So we were assuming that this jump only happens with frequencies exactly equal to EUL by H. If frequencies at all away from that, there is no transition. But that's not true. There is a finite probability of such transitions happening even slightly away from nu naught. Okay. Uh, so we have so phi Lu, this absorption cross section is equal to. So now we can express B in terms of AUL, which is the more fundamental spontaneous emission uh, uh, coefficient. So sigma Lu equals Gu by GL C squared by 8 pi nu Lu squared. So right, so AUL times phi nu. Now, so if phi nu, so phi nu is something called line profile. Okay. If these transitions are infinitesimally, if the line width is infinitesimally thin, then you can approximate phi nu as a delta function, delta nu minus nu naught. So when you integrate sigma uh, d nu, you just sort of substitute wherever there is nu, you substitute nu equals nu naught. So, but phi nu need not be a delta function, and you can actually have, so phi nu uh, is something that sort of quantifies. So schematically, it would look something like this. So you have a sharply raised, sharply peaked function at nu equals nu naught. Nu naught corresponds to this EUL, right? So there is a very high probability of this transition happening at that energy difference. But if you're slightly off from it, it is also non-negligible. So this is like a frequency width of this line profile. Okay. Okay, so this is line profile, and line profile is defined such that phi nu d nu equals 1. The area under the curve is 1, and if the line is very sharp, phi nu is sort of like a delta function, right? Delta nu minus nu naught d nu is just 1. Okay, so this is about line profile. Okay, so yes. Yeah, so line profile in any transition, right? So if you have a bound transition in atoms, ions, or wherever. That's right. So this is the intrinsic, yeah, if the atom is at rest, that's what we are considering right now. We will actually do all that. No, that's the beauty of it. This we derived from LTE. The relation between A, B, and so on, we derived from LTE. But those apply to A, B in all conditions. Yes, yes. And that's the beauty of detailed balance. Detailed balance allows you to relate the rate of, like, the rate coefficients of forward and backward reactions. And those expressions apply even in extreme non-LTE conditions. But you relate them by demanding that if they were to obtain LTE and produce a black body spectrum, then the A and B have to be related by this way. So, these A, B sigmas apply even very far away from equilibrium. So this is absorption cross section. All these are proportional to each other, right? All these are proportional to ultimately to A. B's are proportional to A. Sigma is proportional to A. There is something called an oscillator strength that's also used to characterize the strength of a transition, right? So different transitions have different strengths. So, right, at some point we were talking about uh, allowed transitions, semi-forbidden transitions, forbidden transitions. So the allowed transitions have large values of Einstein's A's. So they have very fast spontaneous decay. Similarly, if you uh, emit efficiently, you also absorb efficiently. That's because of this detailed balance. So all those are proportional to A. So oscillator strength is another way of quantifying the strength of these transitions, which is used sometimes. So this is the definition of oscillator strength. So FLU so oscillator strength of transition from L to U is defined like this. So this is equal to MEC by pi E squared integral sigma LU nu d nu. So this is averaging over the line profile. And this is a dimensionless number. This is a dimensionless number, which is called oscillator strength. And you can actually see that this will also be proportional to AUL, right? So by using these relations, we also know that sigma LU is equal to pi E squared. So if we express the pi E squared by M E C F L U times phi nu. Right, so just from this equation, we can relate sigma LU and FLU in the following way. So pi squared by MEC FLU times psi nu. So this is the frequency dependence. So yeah. So the frequency dependence of the cross section goes in the line profile. Line profile is actually extremely important, and we will actually come to that now. So what I'll do is, since there's lag happening, I will start a new page and start writing here. 27? 24. Anyway, we'll figure that out. I don't think we have had 27 lectures. I think those numbers are just wrong. Yeah. So let's see. So line profiles. So line profiles are extremely important. Line profiles. This concept of line profiles is extremely important. So and there are like, so let's see. So there is something called an intrinsic line profile. So sigma intrinsic, which is a function of frequency. Why is it still lagging? Is equal to pi e squared by MEC times FLU times psi intrinsic nu. So if you have, some energy level, okay, its energy is not perfectly sharply peaked. Okay, it has some width around that energy, and that sort of width makes these transitions happen slightly away from nu equals nu naught. So there is like a so delta E delta T is greater than so there's an uncertainty principle in space. There's sort of a similar kind of an uncertainty principle in time. So delta T can be thought of as the lifetime of a state. If the lifetime of a state is very, very long, like if you have a photon prepared in that particular state, and if its lifetime is very, very long, your delta E is very small. The width in energy of that energy level is small. Okay, so this is this sort of a line width corresponds to the intrinsic line profile. So normally the intrinsic line profile is given by a function which is Lorentzian. So right, so in reality, what you will have is you'll have all these energy levels will have some diffuseness. It's not a delta function at that energy, and that diffuseness is related to this uncertainty principle. Okay, and that is what gives rise to this intrinsic width of or intrinsic line profile, which is different from a delta function. So so normally described by a Lorentzian. So pi intrinsic nu is equal to so 4 gamma UL by 16 pi squared. I don't know. Nu minus nu UL whole squared plus gamma UL the whole squared. So this is a Lorentzian function, as you can actually see, right? A Lorentzian function goes like 1 over 1 plus x squared. And if you just write, so a Gaussian goes like e to the minus x squared, right? A Lorentzian goes like 1 over 1 plus x squared. You can actually see it as a function of frequency. This is a function of frequency. It goes like, 1 over 1 plus x squared. So a Lorentzian will have tails. So let's see. So if we draw phi nu versus nu, this is how it would look like. It falls off slowly, like 1 over 1 plus x squared. An exponential, a Gaussian goes like e to the minus x squared. So once you have crossed a sigma, it really falls very, very fast. So in contrast, the other guy would just fall like this. And it just goes to zero, essentially to zero at large values of x. What? Yeah. The Gaussian peak should be above it. They are normalized. So yeah, that may be true. Yeah. The peak the peak is not normalized. The area under the curve for both of them is the same. Okay, so this is the Lorentzian. And of course, H times nu UL equals EU minus EL. Okay. So this is sort of, let's see, if you're so as gamma UL goes to zero, this is sort of a gamma has a dimension of frequency, right? So this is, if where do you obtain a Lorentzian? If you recall your basic physics courses, if you do this like model for an atom with the forced harmonic oscillator kind of a model, right? If you have x double dot plus gamma x dot plus omega naught squared omega naught squared x is equal to some forcing. This is like a forced oscillator. You get a response function which is like Lorentzian, right? For a damped harmonic oscillator, you get a Lorentzian as a frequency response. Okay, so that's how you justify it. And this gamma there sort of quantifies the width. So in frequency, so this gamma UL is the width of this Lorentzian. So if gamma is very, very small, the width in frequency space, it's very peaked. It has a high Q factor. And so limit gamma UL going to zero, this just becomes a delta function. Okay, so this is Lorentzian. No, because the dimensions of phi nu is 1 over frequency. So phi nu d nu integrates to 1. So the dimension of phi nu has to be 1 over frequency, right? So phi nu d nu is equal to 1. So phi nu is 1 over frequency. So that's what the dimension of this is. And you can actually see if you integrate it with d nu, you will get 1. Okay, cool. Is sort of the width. It sort of defines the sharpness of the energy level. If the lifetime is long, gamma is small. If the lifetime of a state is long, your delta t is long, so your delta nu is small. Right. So that sort of is the sharpness. Okay. Right. So a lot of times we actually go back and forth from frequency space to velocity space. Okay, so we can convert the width in frequency space to a width in velocity space. So delta V, right? So this is the width that I just marked here in frequency space. Like this is sort of like a delta nu. The width in velocity space, intrinsic, and FWHM, the full width at half maximum, is equal to C times delta nu intrinsic FWHM divided by nu naught or nu UL. Right, so this is just delta nu by nu equals V by C. This is what you're using. So that's the mapping between frequency space and the velocity space. This is frequency. Then this, right? So you also know that C equals lambda times nu, right? So we can actually express 1 by nu in terms of lambda. So what we have is lambda UL times gamma UL by 2 pi. Actually, the FWHM, basically the full width at half maximum of this Lorentzian, you can actually see, right? At what value of this delta nu is basically this 16 pi squared times this squared is equal to gamma UL squared. That's when it will have, so when this term equals gamma UL, that corresponds to half width at half maximum. So you double that, you get the full width of half maximum. That would just be gamma UL by, so delta nu, this delta nu would just be gamma UL by 2 pi. You can actually see that. So what is meant by, so if you have some line profile, something like this, full width at half maximum is you go to the half the value of the peak, okay? And just look at what is this. This is FWHM, right? Full width at half maximum. Full width at half maximum. So at nu equals nu UL, this will just be 4 by gamma UL. But we want it to be half of the maximum. So that would be 2 by gamma UL. That just means that this term and this term are equal, and you can do the maths. Simple. All right. So if we plug in the numbers, what do we get? So we get 0. So the intrinsic velocity width is 0.0121 kilometer per second for a Lyman alpha transition. So lambda UL, gamma UL by 618 centimeter. So these are, if we plug in the parameters for Lyman alpha transition, right? So the n equal to 1 state to this Lyman alpha. Right, so n equal to 1 state to n equal to 2 state transition. These are the values of lambdas and gammas. And what you see is that the velocity width corresponding to the intrinsic line profile is 0.01 kilometers per second. Like typical ISM velocities, right? So even if you go to 1 Kelvin, right? So 100 Kelvin is 1 kilometer per second. So 1 Kelvin will be 0.1 kilometer per second. The velocity width, the thermal velocity width for 100 Kelvin is 1 kilometer per second. For 1 Kelvin, it will be square root of t, so 10 times smaller. So 0.1 kilometer per second. This is 0.01. So this intrinsic line width is actually very small for typical transitions. Okay, so this is just the point of this calculation. So this was intrinsic line width, but as we sort of heard, there is something called Doppler broadening. So in a general distribution of plasma, you have atoms and ions moving at different velocities, like a Maxwell-Boltzmann velocity distribution. In that case, the atom will absorb and emit at a wavelength which corresponds to the transition in its own rest frame, right? So if you have radiation and if an atom is moving towards this radiation, and if say it's a hydrogen atom in ground state, the Lyman alpha transition will happen not at nu naught. It will happen at a slightly uh, lower frequency, because the effective frequency that this atom moving towards this light sees a higher frequency. Okay, so this is what happens. So if you have a realistic distribution of velocities of atoms, then uh, you have this Doppler broadening because of absorptions at different rest frequencies of those moving atoms. Okay, so let's talk about Doppler broadening. So PV is equal to 1 by 2 pi sigma v. So this is just the PDF, the line of sight velocity distribution function corresponding to Maxwell-Boltzmann distribution. So 1 by 2 pi sigma v e to the minus v minus v naught whole squared by twice sigma v squared. Right. So this is a normalized Gaussian PDF for one dimensional distribution of speeds. Right. So v equals v naught corresponds to the bulk velocity, and there is a spread around this bulk velocity due to, say, temperature. The molecules have some temperature, so on top of this bulk velocity, they have thermal spread. That is quantified by this sigma v. And sometimes there is something called Doppler B parameter is used. Doppler B parameter is used, and that is nothing but square root of 2 times sigma. So in terms of Doppler B, this is just 1 over square root of B e to the minus v naught whole squared by B squared. This is just a common, this square root of 2 pi form is the standard form of a normal distribution function. But sometimes people use this in terms of B, especially in this literature. So you should be aware of this B. B is nothing but square root of 2 times sigma v. Sigma v is the line of sight velocity dispersion. It's not the 3D velocity. It's sort of, if it is an isotropic gas with random motions equal in all three directions, sigma v will be 1 by square root of 3 of the three-dimensional velocity dispersion. Okay, this is Doppler B. And this is actually also equal to twice kT by mu mp, or the particle mass. So mu mp is the particle mass. So this is this. Right. So this is nothing but the Boltzmann factor if you look at it, right? It's e to the minus e by kT. E is nothing but half mv squared. So that's why you have this half. So you can read it off. So if you have a velocity distribution function like this, and if the intrinsic line profile is infinitesimal, right? That we already saw it's only 0.01 kilometer per second. So for a lot of cases, you can just ignore intrinsic width relative to the Doppler width, and in that case, so you have this. This is basically nothing but. Sorry, my drawing is not good. It should be exponentially. It should be suppressing much faster at large values of velocities. Right. Um, so delta V of FWHM for this velocity distribution PV is what? So when does it become half of it? So at V equals V naught, it is 1 by square root of 2 pi sigma V. So it becomes half of it when this exponential term is equal to half, right? When that e to the minus delta nu squared by 2 sigma V squared becomes a half, that is what corresponds to half width at half maximum. Right, so delta V of full width half maximum is nothing but d8 times log 2 times sigma V. So what I'm doing is I'm just equating this to a half. You take log on both sides, you get delta nu is equal to square root of 2 sigma V times log 2. Anyway, you know how to do this. This is trivial. So this is the velocity width. This, when it becomes half, this is your delta V FWHM. Okay. Now, if you plug in the numbers for this, what do you get? You get as I already mentioned. So sigma V is nothing but square root of KT by M. Okay, so that's nothing but 9 kilometer per second. Temperature T4 is in units of 10 to the 4 Kelvin. So if temperature is 10 to the 4 Kelvin, T4 is 1. If temperature is 10 to the 8 Kelvin, T4 is 10 to the 4. Okay, so T4 by M in the atomic mass units to the 1/2. So sigma V is about 10 kilometer per second for a gas at 10 to the 4 Kelvin, right? And much larger than 0.01 kilometer per second that we considered due to intrinsic broadening. And B is nothing but square root of 2 times this, and that's just about 13 kilometer per second for the same values of T and M. This scales in the same way. It's useful to know this. It's actually useful to know that the one-dimensional thermal dispersion velocity is about 10 kilometer per second for a 10 to the 4 Kelvin plasma. This comes out in very handy, just to feel that, okay, at 10 to the 4 Kelvin gas, the one-dimensional line of sight velocity dispersion due to temperature is about 10 kilometer per second. Okay, now if you have both intrinsic broadening and thermal broadening, then you have to, right? So here, when we just consider Doppler broadening, we just said that, oh, the intrinsic broadening is very, very, the intrinsic line profile is extremely thin, and the broadening is dominated by the velocity dispersion. But in general, you will have to consider both these effects together. So how do we do that? So that brings us to something called, okay, we have considered the intrinsic line profile, which is a Lorentzian. We have considered a Doppler broadened line profile, which has a wider width, but the strictly correct treatment should be something called Voigt profile, VOIG. So Voigt profile is the true line profile. What is written inside here? Here, this is T4. T4 is the temperature in units of 10 to the 4 Kelvin. M is the atomic mass in AMU. So if it is hydrogen plasma, M is just 1. If it is oxygen, this should be 16. Okay. So Voigt profile. So how do we get Voigt profile? So Voigt profile is basically you have to consider Lorentzian for each atom with its velocity spread. So basically, it's a spread. So it's a combination of intrinsic broadening and Doppler broadening. Let's see how do we do it. So let me write down the line profile. So phi nu Voigt is equal to, okay, so let me write down something and then I'll explain how we justify it. So dV times PV. This PV is this probability distribution of line of sight velocities. PV by intrinsic at a frequency nu minus nu UL times 1 minus V by C. Okay, so what have I written there? So every particle with line of sight velocity V will have an absorption probability which will be peaked at a frequency. So nu peak for absorption for a particle with velocity V will be nu naught times 1 minus V by C. So let's see. So a positive velocity is redshift. So this is sort of the convention in astronomy. If V is positive, the stuff is moving away from us. So if something is moving, if a bunch of atoms is moving away from us, it should right. So this right. So so if V is much less than C, this is the frequency that that these atoms will see of the radiation, which is at nu UL. So if you have a intrinsic frequency at nu UL, and if these atoms are moving, they will see. They will absorb. So if atoms are moving towards the source, they will absorb a frequency which is lower frequency. If the atoms are moving away from the source in their own rest frame, they will absorb in their own rest frame, they will absorb at the intrinsic weight, but that is related to this velocity through this. So what you're doing is you're adding up the probability, the probability of having a line of sight velocity V and weighing it with the intrinsic line profile corresponding to the frequency that is seen by that atom. Okay, so it's sort of a convolution of Lorentzian and Gaussian. And so it's sort of, this is a function of V. This is also a function of V, but shifted. So it's a convolution. So phi intrinsic for gamma UL. So it's in the previous approximation. What we are saying is we're just replacing phi intrinsic by delta function. If you do that, in the previous approximation, when I said that the Doppler width is 10 kilometer per second, but the Lorentz width is 0.01 kilometer per second, you are essentially replacing this by a delta function. And what that does is wherever you have nu, you just replace it by this quantity. Or wherever you have v, you replace it by, such that this argument is 0. Mathematically, this is what you'll be doing in that case. So 16 pi squared nu minus nu ul squared plus gamma. Okay, so what are you doing? So now instead of this is a function of nu and nu ul. So instead of putting in nu, you plug in nu is equal to nu minus this guy. So what do we have? We have the other thing is nu naught. Let me say nu naught minus nu ul by nu ul is equal to minus v by c. Okay, so let me actually explain what I am writing here. So nu naught. So if v is the line of sight velocity of a particle, nu naught is the resonance frequency seen by the particle, seen by atoms. Right. So if v is positive, the gas is moving away from us. So nu naught is less than nu ul. Right. So that's sort of, you have to be careful with the sign. A positive velocity should correspond to redshift. So what you have to do is just, this is nothing but nu naught. This is nothing but nu naught. So nu naught is equal to nu ul 1 minus v by c. Yeah, sorry, there's nothing there. This is just v. Okay. So this is phi intrinsic nu minus nu naught. Nu naught is the frequency. Nu naught is the resonance frequency seen by the atom, which is moving with velocity v. So there is a one-to-one mapping between nu naught and v. Okay, so this function, it depends on frequency, but you're averaging over velocity. So you have to you have to be a little careful about what you are integrating over. Okay, so you're integrating over nu naught essentially, or nu naught is one-to-one correspondence with v. You're not integrating over nu, because the final function is a function of nu. Okay, let's do it. So if we plug in things, so phi nu Voigt is equal to. So now if we plug in the phi, the FV, the 1D velocity distribution function, so you get 1 over 2 pi integral dv by sigma v times e to the minus v squared by twice sigma v squared. Right. So this is the line of sight velocity dispersion. So we are assuming that there is no bulk velocity relative to us of this gas. So that's why it's v minus v naught, that v naught is set to 0. And then we have the line profile. So for the intrinsic line profile for gamma UL by 16 pi squared nu minus nu UL times 1 minus v by c, the whole squared, plus gamma UL squared. So we have actually plugged in everything. We have plugged in the one-dimensional velocity PDF. We have plugged in the intrinsic line profile centered at nu naught, which has this redshift taken care of. Now this is an integral. This is not analytically doable. This integral of the convolution of a Lorentzian and a Gaussian is not analytically doable. Okay, so we actually generally take various limits. So, for example, the first limit is where gamma UL, the width in the width of the intrinsic profile is much less than B is B by C times nu UL, right? B is this Doppler B parameter. C is the speed of light. So this is, B was the width of this Gaussian, right? Or sigma V is the width of this Gaussian. So B is just square root of 2 times sigma V. So delta V by C times nu is the frequency width. So if the intrinsic line profile width is much smaller than this, then you can actually replace this by a delta function. This is what we actually did. And if we replace it as a delta function, so this, if we write it as delta of nu minus nu UL, it's 1 minus B by C. And then we integrate this. All you have to do is then, appropriately replace V by nu minus nu UL and things like that. Okay. If you do that, what you get is phi nu is approximately equal to 1 by square root of pi 1 by nu UL times C by B times e to the minus V e to the minus of V squared by B squared. So see, this V is not the, we have already integrated over V. This V here is just something which we are just writing frequency in terms of that V. So B, of course, is square root of 2 times sigma V. And from this delta function, V is nothing but what sets this to 0, right? So V is equal to uh, come on, nu minus nu UL C by nu UL. Right, so if my V is that, so basically this V is not a velocity, it's actually this frequency. You got it? Because phi nu is a function of frequency. The limit of integration is minus infinity to infinity. For what? No, that's not relativistic. That's non-relativistic formula, right? No. This is non-relativistic Doppler shift. The velocities in the interstellar medium are maximum 1,000 kilometers per second, which is much less than c. No, this is just, I mean, this is just, this is just like, what you even apply for sound waves. You can actually apply this exactly for sound waves. Yes. Right. We are writing delta nu by nu equals V by C. This is what we are doing. This is extreme, this is non-relativistic Doppler shift. Right. So whereas the relativistic one is nu equals gamma nu naught 1 minus whatever, the beta, beta parallel, something like this, right? When you put gamma equals 1 and V by C small, that's what you get. That's right. But when you are in the non-relativistic regime, they are sort of to the first linear order, they are all the same. Yes, absolutely. Oh, because this exponential will just kill everything, and which is at large velocities. See, when we do like Maxwell-Boltzmann distribution functions, and there is no C there, all we do is the point is there is no contribution for particles which are very fast. They are exponentially rare. I mean, yeah. We do this all the time, right? When we do velocity, when we find the average velocity of particles, we do these integrals from minus infinity to infinity. Or if we sort of convert it into a absolute the speed distribution, you do 4 pi v squared dv, and there v goes from 0 to infinity, right? Here also, all this is Newtonian. Yeah, so that's what is Newtonian, right? This one, I mean, we do this all the time, right? When we do particle distributions, we put the limits to infinity because there is nothing coming from those high velocities. Those are exponentially rare. Those particles are exponentially rare. They don't contribute anything. And we can actually talk about it. So the other regime. This is the Doppler regime. The other regime is when your nu minus nu naught, so you're very far away from the resonance. So nu minus nu naught is much greater than your sigma UL, of course. But also your thermal velocities, you are much greater than sigma UL, of course, but also B by C times nu UL. Oh, the nu naught is like nu UL. So what am I saying? So what I said is the intrinsic profile has these 1 over 1 plus x square kind of tails. Now my thermal width is this much, my intrinsic width is this much. But if I am at a frequency which is very, very far away from nu naught, right? So the exponential has just gone down. The exponential has decayed to very small value by that frequency, and your absorption is determined by the tail of this Lorentzian. In this case, what do you do? In this case, what you do is you substitute the so in this case you assume PV to be a delta function. You assume the thermal width to be negligible. And in this case, what you get is phi nu Voigt is equal to 1 by square root of 2 pi 4 gamma UL divided by 16 pi squared nu squared. So instead of nu minus nu naught squared, I've just written 16 pi squared nu squared because nu is much bigger than nu UL. So you are really in the tail of this Lorentzian. And of course, this is also very small. This is also very small. Right? So this is small relative to this. So in this case, phi nu Voigt, and then of course you have this integral dV by sigma V e to the minus V squared by twice sigma V squared. This is like treating the particle velocity distribution function as a delta function. Essentially, this will give you 1. You have integrated over the delta function, which gave you 1. So your Voigt profile in the tails is given by this expression. So you can ignore this. So this is how it looks like. And you can actually write this as, so yeah. So in this case, this is your intrinsic profile, and your sigma is about, pi E squared by ME C times FLU times 4 gamma UL by 16 pi squared nu squared. This is your absorption coefficient as a function of frequency. See, this absorption, the frequency dependence of the absorption coefficient was all in phi nu. Right? Everything else was a prefactor. So the frequency dependence goes like this. This applies only in this limit. When the frequency is very high and you're very off the resonance and into the Lorentzian damping wings. Okay. So we will actually come to these things in the next class. Now I'll stop here.